It's mid-August when I'm recording this, and there's a lot of articles in the news about the recurring nova T Coronae Borealis erupting in September. This might sound familiar, as there was a similar stream of news about this in June. The reason for this is that there was a paper that was published last year that predicted the nova eruption on 2024.4 plus or minus zero point 0.3, which corresponds to June through September of this year. Now, it might erupt tomorrow, or it might erupt in September, or it might erupt later than this. I read through the paper that was published in 2023. Though I'm not a professional astronomer, the abstract is usually easier to understand, and then at some point I start skimming by the really technical stuff. But anyway, I'll explain how the author came up with this prediction, and why it might be later than that, so that you don't have to read through the whole thing yourself. Links to this paper and another paper I'll mention are in the description. So first, let's do some back-of-the-napkin calculations. By the way, there are chapter markers if you want to skip ahead. Here are the dates of the known eruptions. The bottom one is a little sus because it was recorded by a monk and we have it secondhand from another writing. Quite a few civilizations watch the sky for omens, so there are pretty reliable records going back thousands of years, especially for new stars and comets. We only know of 6 recurring novas with time spans that are short enough that we have been able to see them more than once. This is the brightest of the 6 and will be a fairly bright star in the night sky, but if you're not familiar with the usual stars in the night sky, you wouldn't notice it. So it's not that surprising that this wasn't noticed from the 13th through the 17th century. This gives us a much longer time span to work with, and we have very few data points, so we'll include it. If we subtract the dates, we can see that it recurs every 29,000 days or so. 29,172 plus or minus 319 days to be precise. So generally speaking, its period has varied by roughly a year. It doesn't erupt like clockwork. Astronomers, however, not surprisingly, use more detailed methods than we just did. When we observe this nova, we are looking at the orbit of the red giant and the white dwarf from a 67-degree angle, and the red giant is teardrop-shaped because a lot of its mass is pulled towards the white dwarf, just to a lesser degree than the mass that gets pulled from the red giant entirely, and then forms an accretion disk around the white dwarf. So, when the stars are perpendicular to us, the apparent area from the star from our angle is largest, and therefore it appears more luminous than when the teardrop is either slanting towards us or away from us. This gives us a reliable benchmark for the star's brightness that isn't polluted by flares, etc. Also, there's a general trick for removing variations that are caused by dust between astronomical objects and us. Dust absorbs more light towards the red end of the spectrum, so these light curves are taken in both green and blue-violet light, and the green light is more affected by the dust than the blue-violet, and so we can remove the variations due to dust as well. There are other causes for changes in brightness that are less well understood. White dwarfs are made of mostly carbon and oxygen, because that's about as far as the fusion reaction gets in the core of the originating star when it runs out of enough fuel to keep it from collapsing and then ejects its outer layers of gas. Besides the carbon and oxygen, all white dwarfs also have atmospheres. The atmospheres are either pure hydrogen or some mix of hydrogen, helium, and maybe a couple other elements. As the mass from the red giant accretes onto the white dwarf, some amount of fusion can occur, just not enough to cause a runaway reaction. There's certainly a lot of interesting processes to study already before the eruption, because this star has been watched so closely over the years. From previous eruptions, especially the one in 1946, we've seen that there is an increase in brightness, followed by a dip, and then of course there's a large spike in brightness when the runaway fusion reaction occurs on the surface of the white dwarf. Then there's a second smaller increase in brightness that is not well understood. The increase in brightness that is expected before the eruption occurred around 2023.25, so late April of last year. At that time, the eruption was predicted to be at 2025.5 plus or minus 1.3 years. So anywhere between March of 2024 and August of 2026. But the light curve increased slower this time than in 1946. Once again, there's a link to this paper in the description. Then, the paper from late last year details the observations of the pre-eruption dip. The link to that paper is also in the description. That paper notes that the light curve from the dip looks exactly the same as the dip in 1946, and so the estimate that the eruption will happen by this September assumed that there would be the same amount of time between the dip and the eruption as there was in 1946. Whether the fact that the white dwarf brightens slower this time means that the eruption will be later is something we don't know, which is why this star is being observed so closely already. We don't know of any other indicators that will occur before the eruption, so we'll just have to wait and see when this nova erupts.